On to electric currents and magnetic fields. Remember at the beginning of this chapter we talked about how closely related magnets and electricity are to each other. By the end of this, we will know that an electric current produces a magnetic field. A moving charge produces a magnetic field. An electric current passing through a conductor produces a magnetic field because it has many charges in motion. The magnetic field surrounding a current-carrying conductor can be shown by arranging a magnetic compass around the wire. The compasses line up with the magnetic field produced by the current, a pattern of concentric circles about the wire. So, what this is saying is if you have a wire, and in this wire you have electricity running through it. As electricity is running through it, you're going to get this magnetic field in a circle around where the current is. When the current reverses direction, so current was going this way, and then all of a sudden it goes this way, the compass turns around, showing that the direction of the magnetic field changes also. I talked to you about the first right-hand rule. So if our current is going this way, current going this way, in this instance, the magnetic field is wrapping around the wire. If the current is going this way, now the magnetic field is wrapping around the wire. In the first instance, it was coming towards me. In the second, it was going towards you because of the direction of the current. When there is no current in the wire, the compasses align with Earth's magnetic field. When there's a strong current in the wire, the compasses align with a stronger magnetic field near the wire. If the wire is bent into a loop, the magnetic field also becomes bunched up inside the loop. When you have this looping of wire together and then you get this magnetic field, that's a transistor. So you have a whole bunch of wire with electric current running through it going in a circle. That is a transistor. If the wire is bent into another loop, the concentration of magnetic field lines inside the double loop is twice that of a single loop. So the more loops you have, the stronger your magnetic field is getting. Magnetic field intensity increases as the number of loops increases. A current-carrying coil of wire is called an electromagnet. Iron filings sprinkled on paper reveal the magnetic field configurations about a current-carrying wire. So this is a current-carrying wire going through a blue piece of paper, and then there's magnetic filings, or iron filings around it. Here is the loop. So now, rather than a straight line wire, now the wire is coming out of the blue piece of paper and going into the blue piece of paper. And you can see these circular patterns, just like here. We get a circular magnetic field pattern. Then if there's a whole bunch of loops, you can see where the magnetic field is lying. Right through it. So a variation of that right-hand rule to figure out what direction is the magnetic field. In a wire, we said the thumb pointed in the direction of the current, and then we could wrap our hands around it, and that will tell us the direction of the magnetic field. For this, we would use our fingers and put our fingers in direction of the current for this, for a whole bunch of loops. And the direction of the current will then reveal the direction of the magnetic field, which would be the thumb in this instance. Sometimes a piece of iron is placed inside the coil of an electromagnet. The magnetic domains in the iron are induced into alignment. So they're forced into alignment, increasing the magnetic field intensity. Beyond a certain limit, the magnetic field in iron saturates, so iron is not used in the cores of the strongest electromagnets. A superconducting electromagnet can generate a powerful magnetic field indefinitely without using any power. Crazy. At Fermilab near Chicago, superconducting electromagnets guide high-energy particles around the 4-mile circumference accelerator. This is a particle accelerator, and what physicists have done is used these superconducting electromagnets, and they speed up these protons and or electrons and a positron, and they speed them up using these magnets, because an electron is going to be forced to move in the field of a strong magnetic, in the presence of a strong magnetic field. So when they do this, they're able to speed up the electron to near the speed of light. And then they can have a positron, which is the opposite of an electron. Everything about it is the same except for the charge, and have it go around the other direction. And then, once they get the speed high enough, they can crash them together. And when you have an electron and a positron crash into each other, or matter and antimatter crash into each other, they are annihilated and all of the energy is released. That's some of the more recent physics. A lot of what we do is done in the 1800s. We're starting to get to the point where we can start talking about things that happened in the 1900s. Superconducting magnets can also be found in magnetic resonance imaging, MRIs. Some of you may have had MRIs. That M is magnetic, just using a superconductor. Why does a current-carrying wire deflect a magnetic compass?